So this is a quick overview of Stoichiometry Fitter. The idea is you input an elemental composition, either atomic weight or oxide percent, or if it's TEM measurement, you can do counts, and then you can apply K-factors and a thickness correction if you want. In the simplest form, you can say you have silicon, compute oxygen by stoichiometry, you're going to get silicon dioxide. So silicon charge is 4, and the oxygen charge is -2, so it'll just figure that out, and that'll automatically normalize everything. Boom, 100% silicon dioxide. Now, really, you would want to do something more complicated. These could be actual atomic percents or weight percents, depending on where your source of the data is from. Here, this is olivine now. And you could even compare it against a solid solution. So say it's forced right to phthalate, that tells me it's Fo50. And that's a really good fit. So you could, for example, do pyroxene triangles with the possibility of excess SiO2 in your spectrum. This is commonly happening in stardust samples, and you can define your own phases. So here, it's very simple CSV. You just give it a name, and then you give it a composition. You can make any phases you want. You just change that CSV, reload the program, and it'll show up in this list in the order that it is in the CSV. All right, so now we won't do that fit. A good example of where this can get really fancy is that these phase, space, and then some name, phase olivine, phase pyroxene ideal, phase spinel, are what generate these. So olivine, I can do a full phase analysis for olivine. And in this case, it's really just computing phone number again and how many cations per oxygen. But you could make that very complicated. And for some phases I have. And all that you're doing is you want to have in that Python file this function. It needs to be called analyze phase, and it takes a vector of atomic weight and oxide percents. You do have to have numpy. But beyond that, anything you do in here is whatever you feel like doing. You can just compute. Here I'm doing the computation of cations for 4 oxygens. And okay, so that's fine. Now let's see how it can get fancy. We can open. This is a file, which is a CSV file. So I'll call this whole object stoichin.csv, which is here. And all this is it's a file that can be produced by some other software, or you can write it by hand if you want, or once you've entered the numbers here, you can save it to produce it. And so this says that it detected 49,000 counts in oxygen, 29,000 in magnesium, and so on. This is from a TEM. So now here you go. And I happen to know that this was acquired at 80 keV. And apply a thickness correction that I know. Compute oxygen by stoichiometry. And I'm going to compare this against various astromaterials. And now it goes off and does a whole bunch of computations and even produces a graph. So here it's computed elements ratio to the average abundance of elements in our solar system. Here gives a reference for it. And then you've got a plot here. The red is the data from this spectrum, and then the blue is a certain type of astromaterial, and the green is another kind of astromaterial. And so you can see, you can do fancy analyses. All right, that's a quick overview.